a look at today's lesson. We actually have two topics today. The first one is algebraic substitution, and the second one is a version of Riemann sums. So let's work on the first one, algebraic substitution. So when we do a U sub, we figure out what we want to make U, then our derivative is there, and everything just kind of clean wipes, it's all U du. There are some instances when we do that where we actually have some x's left over. And doesn't necessarily mean that U sub won't work, it just means that you may need to try algebraic substitution. It's really kind of like a second substitution. So we'll do the regular U substitution, and then we will actually substitute again. So let me kind of go through the process and show you. It's like on the first one. So we look at that and we think, okay, well, U is 2x minus 1, right? That's what we would make U. So U would be equal to 2x minus 1. Then du would be 2 dx, so 1/2 du equals dx. So let's kind of go through here. We would have this portion would be taken over by the u, and then this dx would be taken out by the 1/2 du, but notice how we have an x left over. We have an x left over. When that happens, we should try this algebraic substitution technique. It won't always work, and if it doesn't, that means we need to try different, which we'll learn next semester, a different integration technique. But what we would do is try. So what we have established here is a relationship between u and x. Our substitution, we related u and x together. I've used this portion of it. But what if I solve for x? Then I would get an expression with u in it. So that's actually what I'm going to do. That's the algebraic substitution. I'm going to take this and solve for x, and then replace this x with what I get, and see if it works. Okay, so let's do that. So we would have u plus 1 equals 2x, where x is 1/2 u plus 1. All right, so now this portion right here, this piece is going to go replace that x. And we're going to take that and we're going to put that instead. So what I have this 1/2 from my u sub portion, and I have this 1/2 from my algebraic sub portion. And I'm going to put them outside the radical, or outside the integral. So we're basically going to have a half times a half, or 1/4. So we have 1/4 outside there. So replacing the x is going to be this piece right here. I already have the 1/2 here, so the u plus 1. And then replacing this would be u to the 1/2. So hopefully we recognize we can't integrate it in this form. We're going to need to rewrite it. So I need to distribute. And that's really the only time this doesn't work is if what we have left over we can't integrate. It could happen. This we can actually integrate. We can distribute the u to the 1/2, and we would get, what, u to the 1, so 2 over 2 plus 1 over 2, 3 over 2, and u to the 1/2 times 1 would be u to the 1/2. All good? So now let's do our reversal power rule. Let's go ahead and integrate. So we have 1/4 times, let's see, add 1 to 3/2, we get 5/2, divide by 5/2, multiply by 2/5, u to 5/2, plus, add 1 to 1/2, get 3/2, so plus 2/3 u to 3/2, plus c. Back to plus c. All right, so I'm going to actually do two things at once. I'm going to distribute this 1/4, and I'm going to put the u back in all at the same time. Hopefully that's not too troubling. So I'm going to do that all in one step and get 1/10 times my u is 2x minus 1, 5/2 plus 1/6. 2x minus 1 to the 3/2 plus c. And that is our very first algebraic substitution. How's that? Okay. All right, let's look at our next one. So on this one, 1 plus x squared would be kind of where we would go to do a u sub. So u is 1 plus x squared. So du is 2x dx, or 1/2 du equals x dx. That's my u sub part. So this portion right here is my u, right? And I actually only need 1x for my derivative. I just need one of those. I have 5 of them. So I'm going to have to, let's think about it this way. I have this one I'm going to take care of with this. But the other 4, there's 4 right there, I've got to try to do an algebraic substitution with. I've got to try to get rid of them by looking at the relationship that I've already established between u and x and using that relationship to solve for x. So I'm going to move the 1 over, and since I need 4 x's and there's 2 here, I'm not going to square root. I'm not going to go all the way to x because I need 4 of them and here's 2. So basically I need 2 of these, or I need 2 of those. I would replace those 4 x's with 2 u minus 1's. All right, so let's do that. Let's go through that substitution. So I have this 1/2 from my u sub part. And let's see, then we would have u to the 1/2 in here. And I have 4 x's, so we need 2 of these du. Okay. So at this point, again, we can't integrate it like that. We're going to have to, do algebra. We're going to have to FOIL it, distribute the u to the 1/2, get everything all worked out. And I did that already. I'm not going to go through the algebra, but I had already done that. So when you do that, when you FOIL this out, then distribute the u to the 1/2, you will get u to the 5/2 minus 2u to the 3/2 plus u to the 1/2. All right. So now let's integrate. So we have 1/2 times the integral of u to the 5/2 is 2/7 u to the 7/2 minus 2 times. The integral of u to the 3/2 is 2/5 u to the 5/2 plus the integral of u to the 1/2, we add 1 to 1/2, get 3/2, so 2/3 u to the 3/2 plus c. Okay? All right, so we're just going to do actually a couple things at once. Okay, I'm going to distribute this 1/2, and I'm going to put this u, the 1 plus x squared, back in. Okay, we're going to do all of that at once. And probably have to use more than one line. That's okay. So I get 1/7 times 1 plus x squared, the 7/2 minus, and multiply all that together, and I get 2/5 times 1 plus x squared to the 5/2 plus. Then we get 1/3 times 1 plus x squared to the 3/2, or I might almost say plus c. And we got our plus c. Okay, so that is our second algebraic substitution. All right, let's look at the very last one on here. Move this up a little bit. So here, We think we can see u would be 2x minus 1. du is 2 dx, so 1/2 du equals dx. Okay, so this is going to turn into a u, and I have an x, an extra x. So I'm going to have to try the algebraic substitution again. I'm going to take the relationship that I have between u and x, and I'm going to solve it for x. So let's see, that would be u plus 1 equals 2x, or 1/2 times u plus 1 equals x. Okay. So I have two halves again. I have this half from my u sub, and I have this half from my algebraic substitution, which is going to make a fourth, right? I'll pull out a fourth. Okay, oh, I'm going to have to change my bounds. All right, let's change our bounds. Let's go up here. So let's see, we have u equals 2 times 1 minus 1. That's my lower bound, or 1. My upper bound, u equals 2 times 5 minus 1, or 9. So I have those bound. And again, I think we've talked about this before. You don't have to write out that work. If you want to do that in your head, you certainly can. I'm just writing it out so we're all clear, make sure we know how we got those numbers, right? The 1 and the 9. So I'm going to keep it with u's, and my new bounds are 1 to 9. So let's see. In the numerator, we had 1 plus 1, u plus 1, and the denominator is u to the 1/2. Now we can't integrate that. We've probably encountered those before, where we need to rewrite that. There is no quotient rule in integrals. So if I wrote this as two different fractions, I could do my reversal power rule. So let's just think about it as two different fractions. So 1/4 integral of 1 to 9. So u to the first over u to the 1/2 would simplify to be u to the 1/2 plus 1 over u to the 1/2 would be u to the negative 1/2. And that's what we'll integrate. Right, so we have 1/4 times the antiderivative of u to the 1/2. Let's see, add 1 to 1/2 is 3/2, so 2/3 u to the 3/2 plus, we add 1 to 1/2, and we get 1/2. So plus 2 u to the 1/2. And now this we would evaluate from 1 to 9. Now we have done several days of that, and just for time's sake for the lesson, I'm not gonna do the f of b minus f of a right now and do all the arithmetic. I'm just gonna tell you that if you were to do that, f of b minus f of a, work it all out, you should get 16/3. 16/3 would be the answer that you would get. Okay, now that is our first topic, algebraic substitution. How are we with that? Okay? All right, for our second topic, as I give the board time to erase. So the second topic is, it says Riemann sums. Okay, I have a nickname for it. I call it scary Riemann sums.
Oh,
I know. Scary Riemann sums. Why? Well, as soon as we get to the page, I'll show you why. Now, after I teach this lesson on Riemann sums, some students are so traumatized by the Riemann sums that every time they see Riemann sums, they want to do what you're getting ready to see, the next lesson. But I promise you, the only time that you're going to encounter scary Riemann sums is with the multiple choice question. And there's a chance that you could get a multiple choice question on scary Riemann sums. So I need you to understand it. And I guess it's kind of fitting, right? Scary Riemann sums when my screen to go black. I don't know. Here we go. It's back. Okay. So here we go. Now, so think about, remember the whole definition of derivative? Remember that? Of course we do. It's on the phone quiz all the time, right? Of course we remember definition of derivative. Well, we are looking at the definition of an integral. Wow. Okay, so we know definition of the derivative is a little bit more intense than actual derivatives, right? Than all the rules that we learned. Okay, think about that and then kind of multiply it by 2 for definition of the integral. It's like crazy. Okay, we're not going to work integrals by definition of the integral. And they don't require us to on the AP test. But they will require that we're able to go back and forth, to transform back and forth between integrals and the definition, integrals to the definition. And that's what we're going to work on. Okay, so before I start the lesson, I just want to make sure we understand that we're talking about maybe one multiple choice question. Okay, so there should be no panic or, no craziness. It's okay if this is crazy and difficult. It's really just about formulas. It's just about formulas. Okay, so that's all it is. If you can memorize formulas, you can do straight Riemann sums. So, that's what we're doing. The things we're going to be interested in or need to memorize, we need this formula. This is a right endpoint formula. I've really never seen them use a left endpoint. And so when we're talking about endpoints, we're talking about Riemann sums. Recall when we do the rectangles, and we add them all up. Well, the definition of an integral actually is like taking the limit of the number of rectangles to infinity. Right, the number of rectangles in a Riemann sum. You know how we have 4 or 5? Well, the actual definition of the integral is like an infinite number of rectangles. That's why our integrals are so accurate, because that's how it was based on. We're not going to have to do that, just saying. But this right endpoint is talking about a right Riemann sum, and left endpoint is talking about a left Riemann sum. And really, to be honest, this is what we see is a right Riemann sum. So we need to know this little piece right here. And the other one is the delta x. We need to know that little formula. Those two. This formula is what we want to be able to go from an integral. So this is the definition of an integral. And it would be so fun to go through all of this abstract stuff with you. There's just not time. I know you're upset about that. You wish that I could, but there's not time. All right, so here is my integral, just a regular integral, and this is the definition. It's the limit as n goes to infinity from k equals 1 to n of the function with ck is basically embedded in the function. Like with our derivative f of x plus h minus f of x, right? Those just kind of things. So ck, which is this, c1 is ck, that's that. It's going to be put inside the function. And this is this. And those are the two things that we need. We need this that goes inside the function. Wherever there's an x, we're going to put this formula. And this is going to create this piece for us, that delta x. That's how we find delta x. That's it. Okay? So we're first going to go from the integral to the definition, and then we're going to go backwards. All right. So let's look at this formula. This a means this a. It's not just a random a, it's actually the lower bound. And this b is actually this b, it's the upper bound. Those aren't just random a, b's, they have a meaning. A is the lower bound, b is the upper bound. N is, the number of rectangles we're going to use, which is infinite, but this is just n. Okay, so this is a, and that's b. So what we're going to do is we're going to use this formula right here to find our delta x. So delta x equals, okay, we're using this formula b, which is 1 minus a negative 2 over, and it's over n. So our delta x is 3 over n. Okay, what have we done? We have just found what we're going to put right here. We're going to put 3 over n right there. Okay? The next thing that we're going to do is we're going to work on our ck, or c1. They just change numbers and variables, there's all kinds, doesn't matter. Whatever it is, c sub whatever. That's this. So this A is the same thing as this A. It's our lower bound. So our C1 or CK, whatever you want to call it, is A, which is -2, plus, see, it's I times our delta x. We already found our delta x, so it's I times 3 over n. That's our C1 or CK. Okay. How are we? See, I'm just using formulas. I know it's very abstract, but I'm just using formulas. I found my delta x, I found my CK or C1, and now I'm going to, so I know this, I'm going to substitute this expression right here into the function that I have, this function over here, which happens to be 2 times x. So I'm going to put this everywhere there's an x in my function, and it just so happens there's just one x. So I'm just going to, so we're going to I'm going to start writing this now. We've got all the pieces of the puzzle, we just need to put it all together. So I just copy this down. It's the limit as n goes to infinity, okay, of the summation from k equals 1, and you can use k or I or n, those are just the normal letters that we use. It doesn't really matter, whatever you want. As k goes from 1 to n of my function with this inside. So my function, which is 2 times, this whole part is inside, -2 plus 3I over n. So I have this portion right here. Now I need to multiply that by my delta x, and my delta x is 3 over n. The only other thing that we might do is just clean it up a little bit. Typically what they would do is they would take this little guy and multiply it by the 2. So let's just rewrite. You have to know. You can leave it just like that if you want. It's fine. But let's go ahead and just, hope you see another way you might see it. So the limit goes to infinity of the summation from k equals 1 to n. The n is supposed to be on top here. Then we have 6 over n times -2 plus 3I over n. And that would be the definition. And yes, you could work that out. See, doesn't that look fun? You do the summation of all that, and then you take the limit of that, and then you would get the answer to the interval. Okay, so you can see why we think, oh, that'd be so fun, but we just don't have time. Sorry, we don't have time to do that. So we have just gone from the integral to the definition. Now let's go from a form of the definition to the integral. Typically what they like to do is they like to have it all expanded out like this. Notice the summation is missing. Another way to write a summation is to basically show the first few terms added together, plus dot 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 plus, and then the general term. That's how to write a summation out if you don't want to put the little sigma there. And that's what they've done. The sigma is not there, they just expanded it instead. So if we look up here to our expansion, this is what they've done. They have this part and then this part, plus dot dot dot, and then the general term. That's what they've done. This would be like our C1, that would be like our C2, and that's like our CK. All right, so what I'm going to pay attention to, what I need to pay attention to is this like CK, this thing right here. Okay? So here, this A is this number right here, whatever's here. There's a 5 here, that means A is 5. Whatever's there. If there was a 2 there, A would be 2. If there was nothing there, what would A be? 0, right? It's whatever's there, that's what's A. So I have A. Now look at the way this is formed. So let me go back and show you what's a little troubling. It just troubles me. It may not trouble you. You're probably like, yeah, that's fine. It's not fine with me. So notice how right here we have this little I. Wasn't that nice? It's different than the N. What's different? They don't like doing that. Right? This is the I right here. What? I is the N? Yes. This is the I. Right there. So, you need to know that, or you're going to get confused. I mean, it's confusing anyway, right? So this is the I. So that means that if that's the I, this part's the I, this part, and the delta x is the 3 over n part. So delta x is 3 over n.
Then wait, so like in this situation, is the n equal to I? Like are they the same value?
No, see here we got 1, 2, no.
So it's just like
No, this is not. This is not. Sorry. No, they're in sequence. They're basically moving here. They're using n going to infinity. They're showing it's a 1, 2, 3, all the way up to infinity. Okay, it's different than this n. This n is this n. They could use a different letter, but they don't. Okay? Yes.
wait, is 3 over n is delta x and y is 1 over n on the outside.
Okay, so this isn't delta x. We're getting to it. So hold. Well, we're getting there. We're getting there. So, here we go. So what we're going to do is we're going to back into b. We're going to use this formula. So I know 3 over n is my delta x equals b minus 5 over n. I'm using this formula to find b. Okay. So it's pretty straightforward. There are n's on the bottom. We just need to think about what minus 5 would give me 3. I mean, we're really not a whole lot into it, right? What minus 5 would give me 3? Would be like 8. So b is 8. So I have the integral from 5 to 8 of my function. So my function, this function is squared. The function is x squared. That's my integral. So I want to talk about this 1 over n because it's caused students problems all day long. We know that from this, that is the delta x. But we also know that, so you haven't been involved in the expansion of this, right? How they expanded it, how they made it look. There are all kinds of constants that are involved in it that we don't see. So we don't want to let this not being 3 over n trouble us from this fact right here. This is what we need to focus on. So what happened to the 3? It just got, who knows what happened to it. I didn't expand this. But it's not there. It's not there. So I just want you to focus on this part right here. Right here. Who knows, maybe something had a third and it just got rid of it. I don't know. But this right here is what we're going to focus on because that has this formula in it, where that I is this number and that is definitely delta x. Okay? Period. Just focus on that, don't worry about anything else. Because it's going to look just like this, I promise. They'll just be strange. So don't worry about that. Worry about the general term to get our pieces that we need. Now, I don't really have time to go over this multiple choice question, but this is actually straight off of one of the tests, one of the AP tests. So if you would like to try that one, I encourage you to. I would tell you, just circle the answer for you. This is what you should get when you work through it, is D. So I encourage you to try it. Wherever you see scary Riemann sums, on multiple choice questions, okay? If I give you a free response question on a quiz or test and it asks for a Riemann sum, it is not asking for this. Okay? It's asking for normal, what we did, days ago Riemann sums, right? They're different. It's not asking for the definition of the integral. This kind of Riemann sum is actually the summation of Riemann sums, if we'll be specific. The summation of Riemann sums, the limit of the summation of Riemann sum. That is very complex, right? That is not what I would be asking for in a free response question. Are we okay with that?
Oh boy.